Dinesh MA, working as Assistant Professor in the Department of Electronics and Communication Engineering, Maharaja Institute of Technology, Mysore. I welcome you all to the lecture series of the course Basic Electronics 22BEE13. Module number 1 in this course is the semiconductor diodes and its applications. And in today's session, we'll understand the basics of any diode. A diode is said to be a 2-electrode or a 2-terminal device. And a diode offers low resistance path when it is forward biased, and it works as almost a closed switch when it is reverse biased. And we have different categories under diodes. The lower order current diodes are used to be switches, and the higher order current diodes are used as rectifiers. And we also have something called as Zener diodes, which are used as voltage regulators. Now coming to PN junction diode, this is how a PN junction diode looks like. So a PN junction diode will have a P-type semiconductor material next to N-type semiconductor material, which forms a single junction between the P-type and N-type. And you can also see this will be having two conductors, one connected at the P-type and the other one connected at the N-type. And this is the symbol of PN junction diode. The terminal at the P-type is anode terminal, and the terminal at the N-type layer is the cathode terminal. And this arrowhead indicates the direction of the conventional current that flows through the diode when the diode is said to be forward biased. Now, when the anode terminal of the diode is connected to positive terminal of the battery and the cathode terminal is connected to negative terminal of the battery. On the other words, I can say when anode becomes more positive than cathode, the diode is said to be forward biased, allowing forward current IF flow through the diode. When the polarities are reversed, or when cathode becomes positive with respect to anode, then the diode is said to be reverse biased, where almost zero current would be flowing through the diode. And this current is called as reverse saturation current. Now let us understand the IV characteristics of a PN junction diode. So here we have the VI characteristic plot, and this x-axis represents the forward voltage VF, and this y-axis represents the forward current IF. And the same way here, the negative y-axis, this represents the reverse current IR, and the negative x-axis represents the negative voltage, that is the reverse voltage VR. Now coming to the forward bias condition, as I indicated just now, when the anode becomes positive with respect to cathode, the diode is said to be forward biased. And as we move on increasing the forward voltage across the diode, the current remains almost zero, typically less than 100 microamperes, till the forward voltage crosses 0.7 ohms. As soon as the forward voltage of the diode crosses 0.7 volts, the forward current IF will increase almost linearly. Right? So let me repeat this. Till we cross the forward voltage of 0.7, the forward current of across the diode, or sorry, let me repeat this. The forward until let me repeat this. The forward current through diode will remain almost zero, typically less than 100 microamperes, till the forward voltage across the diode crosses 0.7 volts. once we cross 0.7 volts of forward voltage, then the current through the diode will increase almost linearly. Now coming to the reverse characteristics of the diode, since the diode is reverse bias and the diode is working as open switch, there would be zero current flowing through the junction. So that is typically less than 100 nanoamperes. So it is going to be something like this. And further, if we go on increasing the reverse voltage also, the current remains to be constant through the junction. And when the reverse voltage is crossed a particular point, say for example minus 75, typically the junction is said to be broken and there will be a huge current flowing through the junction. And the point where the junction breaks down, we'll call this point as reverse breakdown voltage. So this voltage is called as reverse breakdown voltage. So at typically minus 75 volts for any silicon diode, the junction breaks down and there will be a huge current flowing through the junction. Now coming to the forward characteristics. So here what we can see is, so when the diode crosses 0.7 volts, there is a rise in the current. There is a rise in the forward current that is flowing through the device. And this, the change in the forward voltage, that causes rise in the forward current, we'll call it as delta VF, and the change in the current, we'll call this as delta IF. And from this, the IV characteristics, we have understood that when the diode is forward biased, it will be offering low resistance path working as closed switch, and when it is reverse biased, the diode offers high resistance working as almost an open switch. So this we can understand with the help of some simple numerical also. Let us say like if IF is equal to, if IF is equal to 100 milliamperes, where VF is approximately 0.75 volts, right? So here we can see that at VF is equal to approximately 0.75 volts, the forward current is 100 milliamperes. Now if we consider these two values as example and use Ohm's law to find out the resistance RF, that is forward resistance, so we know that this is given by VF by IF, and if we substitute these values, 0.75 volts divided by 100 milliamperes, and this would give us a resistance of 7.5 ohms. Whereas in the reverse characteristics, if we consider something like VR is equal to 50 volts and IR as 100 nanoamperes approximately. So using these values with the Ohm's law equation, this would give us RR of about, substitute VR and IR in the equation there, like VF by IF, this would give us 500, this gives us 500 megaohms. So with this example, what we can understand is when the diode is forward biased, it is offering low resistance path. It is offering only 7.5 ohms, so that the diode works as what a closed switch. It allows the forward current IF to pass through it. Whereas when the diode is reverse biased, the resistance you can see here, the resistance it offers is 500 mega ohms. So where the diode is said to be open switch, so there would be no current or approximately zero current, or a negligible amount of current would be allowed to flow through the diode. So this is about the silicon diode. Now another type of semiconductor diode what is available is germanium, where the characteristic of the germanium diode is similar to the characteristic of a silicon diode, but the values will be varied. Now when a germanium diode is forward biased, because the knee voltage or the cut-in voltage of a germanium diode is 0.3 volts, now the forward current would be almost zero till the forward voltage crosses 0.3 volts. As soon as the forward voltage crosses 0.3 volts, again there will be an increase in IF. There will be an increase in IF. So knee voltage of a germanium diode is 0.3. So as soon as we cross 0.3 in any germanium diode, there would be IF flowing through the diode. Now coming to reverse characteristics of germanium diode. So what we have here is the current ratings will not be in nanoamperes in germanium diodes. It will be in microamperes, and typically when a germanium diode is reverse biased, there will be typically 1 microamperes of current that would be flowing through the junction. So this would be the ideal current flows, but the reverse breakdown voltage would be typically around 50 volts. So the breakdown occurs at 50 volts in the germanium diode. So if not, the characteristics of silicon and germanium look identical. Now we'll understand the parameters of diodes, various parameters of any PN diode. The different diode parameters associated with any diode are: first one, the forward voltage VF. This is the voltage where the current starts increasing. So the forward voltage VF. Second one is IR. IR is reverse saturation current. That is, when diode is reverse biased, what is the current that is flowing through the junction? Typically it should be zero. So the reverse saturation current what is flowing through the diode. And third one is VBR. VBR is the reverse breakdown voltage. The voltage, the point where the diode junction breaks down. The reverse voltage at which the junction breaks down is what the VBR. And the fourth parameter with respect to any diode, what we have is RD. RD is dynamic resistance. RD is dynamic resistance. Now, just now we calculated the resistance here in the reverse bias condition and in the forward bias condition. So these are the static resistance or the DC resistance. For given VF and IF values, what is the resistance is what we found out here. But now RD is the dynamic resistance in this given range. So what is the resistance value? So how do we calculate this? This is calculated using the slope of this curve, the characteristic, right? And this is given by the ratio delta VF by delta IF. So this is the ratio what we use to find out the dynamic resistance RD. And the fifth parameter is the IF max. So what is IF max? IF max is the maximum forward current the diode supports. So these are the 5 parameters associated with any diode. Let me repeat this. Number 1 is VF, that is forward voltage drop. So the voltage, the positive voltage at which the forward current starts increasing. So that is the first parameter. Second parameter is IR, that is reverse saturation current. When a diode is reverse biased, what is the amount of current that is flowing through the junction? And third one is VBR, that is reverse breakdown voltage, the negative voltage at which the junction breaks down. And fourth one is dynamic resistance RD, which is calculated with the help of slope of the forward characteristic. And fifth one is IF max. IF max is maximum forward current that is permissible with that particular diode. So these are the parameters associated with any diode. So let me summarize today's session. In today's session, we have understood what is a diode and how does a diode look like, and the symbol, how do we write the symbol of the diode. So a diode is made up of 2 semiconductor layers. One is P type and another one is N type. In between these two there will be a junction formed, and the terminal associated with the P layer is called as anode terminal, and the terminal associated with the N type layer is called as cathode terminal. And the diode is said to be forward biased when anode is positive with respect to cathode, and the diode is said to be reverse biased. The diode is said to be reverse biased when cathode is positive with respect to anode. And we have also understood the forward characteristics and reverse characteristics of both silicon and germanium diode. So during the forward bias, until the forward voltage crosses the cut-in voltage or the knee voltage of a silicon diode of 0.7 volts, the forward current would be almost zero, and as soon as we cross 0.7 volts, there will be a sudden increase in the forward current IF. And the slope is what we consider to find out the dynamic resistance RD. And at any given point on this curve, we can find out the forward resistance, what is also considered to be the DC resistance. And for a germanium diode, the characteristics is almost same, but the forward voltage drop occurs at 0.3. So at 0.3, the diode starts conducting and there will be a current flowing through the junction. Coming to the reverse bias characteristics, the diode current will be almost zero for both silicon and germanium, and it is going to be constant across the scale. And for the silicon diode, as soon as we reach the VBR of 75 volts, there will be a breakdown occurring in the junction. So there is a sudden increase in the reverse current. And this VBR is 50 volts for any germanium diode, and as soon as we reach 50 volts on the reverse scale, there will be a breakdown occurring, and because of that, a sudden increase in the reverse current happens. And these are the diode parameters what we have discussed. So that is all what we have for today's session. In the next session, we'll understand the approximations of a diode and also the equivalent circuits of the diode.